Alright guys, this is going to be lecture 12 and it's going to be about the triple integrals in Cartesian coordinates. The new lecture note is going to be sent to you in the line group and on Canvas too, so you can download the file and maybe study along with this lecture. So triple integrals in Cartesian, it means that we are going to come back to the variables that we are used to, x, y, and z. In the last video, we worked on polar coordinates, which is the radius and theta. This time around, we come back to x, y, and z. I think many of you would be happy to see these three variables again. Alright, before we dig into the triple integrals, let's take a look at the other integrals that we learned in this class and also in Cal 1. So let's start by taking a look at the single integral. In single integral, we have one variable to consider. So we have x, and we perform something like this. We perform integration of function that only has one variable x with respect to that variable x. We did something like this in Cal 1, and by now you should know that this is about the area under the curve fx. It has a physical meaning. Area under curve fx. When function has only one variable, the shape of that is a curve. And when you look at this is about the area. It means that the value out of this is 2D. So this is 2 dimension because this is area. Alright, and now we can also use this single integration to find the average value of a function. We can use this to find average value. Okay. Value of fx. And as you can see, average value, it comes out to be scalar, which means that that value has to be one dimension. So I show this to you because when you see an integration, don't assume that the result has to be area always. Sometimes it comes out to be a scalar. It depends on how you use it. Single integration can come out to be 2 dimension or 1 dimension. Alright, that is what we learned in Cal 1 long time ago. Now, in Cal 2, we learned about the double integrals and something that we just did after the midterm. So in double integrals, we have 2 variables to worry about. So we have x and y here. And as you know, in double integrals, we do the integration twice on a function that has 2 variables, x and y. And what comes after this is not just dx. It's going to be something different, and we call that differential area, dA. Okay, and when it comes to performing integration, you have to specify the region or the boundaries of this integration. So we call that boundaries R, domain region. And some of you might ask, what is dA? Okay, and don't forget that we talked about this already. dA is the differential in x direction, like that, dx, times the differential in y direction, dy. And once you multiply them together, it comes out to be the differential area. Differential area equal to dy dx and also equal to dx dy. You can switch the order of this multiplication, it doesn't matter. Alright, and if you look at the single integral, we have this dx only. So this is like a little change in just 1 dimension. Okay, so we did this just a few weeks ago, and we know that the meaning of this double integration is the volume. Notice the difference between single and double. Single is area, now it becomes volume. Volume under surface function fxy. Okay, when your function has 2 variables, the shape of that becomes a surface or a plane instead of a curve in single variable. And we are talking about volume here, which means that the value that comes out of this double integration is 3D, something we can visualize. Think of the Riemann sum that we did in 3D. Think of all the posts, all these small pieces, and we add together becomes a volume. Okay, and that's what we did in double integration. And we also use some technique. We define fxy to be equal to 1, and if we did this, the result of this double integration becomes area of domain region R. Alright, so the result of this comes out to be area, which means that this value is 2D. Area is 2D, volume is 3D. Just like in single integrals, you perform double integral and you can get either 3-dimension value or 2-dimension value. Don't assume double integral to comes out to be just volume. It can come out to be area too. Depends on how you use it. Okay, now you see the trend that is moving like from single to double, and we are going to follow this trend to the triple integral. In triple integrals, just like you expected, we are going to integrate this 3 times. Integrate this 3 times. Alright, 1, 2, 3. And we are going to perform this integration on a function that has one more variable. Not just x, y, we have z here. So in this case, triple integral, we are going to have 3 variables, x, y, and z. What comes after this function x, y, z? It has to be some certain differential. And we don't know what that is, so let's guess what is it going to be. So let's take a look here. Single integration, this is dx. dx, this is like differential distance, right? Now, double integration, we have dA. This is differential area, 2 dimension, right? This is 1D, this is 2D. Now we move to triple integral. This D right here is supposed to be 3D. 3D, differential in 3D, that is differential volume. Okay, so we have something like this. And let's take a look at the physical meaning. Look at the trend here. We start at the area under the curve, volume under the surface. Now we have to move to 1 dimension more than volume, and it's not something that we can visualize. So I'm going to say that this is some value in 4D. In 4D, and it's not something we can draw it or visualize it easily. Not easy to visualize. Okay, all right, and let's take a look at dV here. Some of you might ask, what is dV? So let's compare to this dA that we have here. This dA, we have dx and dy, and you can expect to have dz in this dV, right? So here we have dx right here, dx, and we also have dy, and we have this dz, sorry. We have this height of this box, dz. So when you multiply all of them together, this becomes differential volume. This little box right here. dV is going to be equal to, well, I'm going to pick one order here. dz, dx, dy. And it's going to be equal to dx, dz, dy as well. So the order can be swapped. It doesn't matter which order you go for. So make a note here, order can be changed. You can pick any order you want here. it's going to come out to be dv just the same. Alright, and now we move back to this triple integral. When it comes to integral, you have to define the boundaries. Just like in up here, we are supposed to find the boundaries for this domain region. Here in triple integrals, you have to do that, and we are going to call that that domain D. It doesn't make sense to call this R again because R is region. Region makes sense in as an area. It doesn't make sense as a volume. So we are going to call this the domain here just D, and just keep in mind that this is in 3D now. Okay. All right, and let's add one more. Just like in double integrals, we can set f, x, y, and z to be equal to 1. If we set x, y, and z equal to 1, then triple integrals is going to be the volume of the domain. Just like up here, you set f to 1, it becomes the area of the domain. Now you set f to 1, it becomes the volume of the domain, with just one more dimension than the double integrals. And this triple integral can be used for something else, such as to calculate the mass and the moments of solid with varying density. Some of you might need to use it later in your other courses, some of you might not, but just take a note here. We can use this to calculate the mass and moment of solid with varying density. Sometimes you are given with density function and you are supposed to find the overall mass of the certain object in 3D. You have to rely on this triple integration. So one more thing, you can use this to triple integrals to find the average value of f, x, y, and z over 3D space, over 3D space. Okay, some of the things that you can do from triple integrals. So first, find the volume, and you are going to run into this quite a lot. We are going to use triple integrals to find the volume many times. All right, and second thing, mass and moment, maybe in physics, but I'm not going to focus on this because I know some of you might not use this later in your other courses. So, and third one, average value of the function itself on 3D space. Okay, that is the overall, like when you compare the triple integrals to other integrals. It's like adding one more dimension to all these meanings. Okay, all right. Now let's move to the formula. What does it look like? Well, of course, you are going to have 3 signs of this integration. All right, and you are going to perform this integration over on the function that is in terms of x, y, and z. And after that, it follows with the differential volume. Okay, and if we leave it to be like this, differential volume, we can't perform the calculation because we don't know how to use the integration directly with the volume. So instead of using the volume here, we are going to pick some order of the integration. All right, I'm going to pick some. Here in this case, I'm going to pick dz, dy, and dx. And keep in mind that this is going to be equal to differential volume. Okay, all right. Now we are supposed to put some values in for the boundaries. This is going to be for the z variable because we have to just like in double integration, you have to work from the inside to the outside. So in this case, you are supposed to integrate with respect to z first, and you have to specify the boundaries for z variable, these two. After that, you integrate with respect to y, and you have to specify the boundaries for y right here. And after that, at the end, you have to integrate one more time with respect to x, and you have to know the boundaries for the x variable. Okay, so you are going to run into two cases. The first one, boundaries are given to you directly. And you are going to see this in an example. What does it mean to be given to you directly? Okay, and if it's in this case, it's going to be easy to solve, because you don't have to find out anything. You just perform the integration 3 times. Easy to solve because you only need to integrate 3 times. Integrate. And of course, when it comes to multiple integration, you have to work from inside out. Make a note here, work from inside out. Now that is the first scenario. The second scenario, that's going to make your life a little bit more difficult, is that the boundaries, all these 6 variables here, boundaries are given to you in terms of object, in terms of 3D shape. Like you see a shape in the space, and then you have to determine all these 6 boundaries by yourself. And I'm not worried about the first scenario. I'm pretty sure that you can perform the integration with not too much difficulty. But the second scenario, it's going to be quite tricky, and it can get confusing really fast. So in this case, I provide you with a guideline to find all these boundaries from 3D shape. This is going to be this guideline. It's going to be for the scenario 2. Alright. So let's take a look here. What do we need to do when we have a shape instead of some specific values given to you directly? Right? Just assume that you have a shape showing up maybe in terms of points, maybe in terms of graph. What do you need to do in order to determine all 6 boundaries? To determine 6 boundaries. 6 boundaries. Okay. On this slide, it might not make sense to you. That is okay, because this is just guideline. But we are going to apply this guideline in some examples later. It's going to make sense to you later. So don't worry if this doesn't make sense at this point. So, first thing you need to do for this scenario 2, always sketch the volume. You need to sketch the graph. On graph. Without seeing the shape, without knowing what it looks like, it's impossible to perform the integration. You don't know where the boundaries are, so sketch it. Right? Second thing, number 2, determine the order of integration. You have to know which variable you are going to integrate first, and then which one is next, and then which one is the last. So if you look at this in this example up here, so you can see from up here that you are going to start from z, then y, and then x. This is the order that you need to know. Alright, now number 3, sweep the first variable. This is about integrating now. Sweep first variable. In this case, is going to be this z. Between two surfaces, that is the key point. Variable between two surfaces. You might ask, what surfaces are you talking about? You'll see what that is. But this is the key word. The first variable has to be done between two surfaces. Alright? Now, the next thing, 4. Determine the projection. Projection means the shadow of the shape of the object onto next to variable. What does that mean? Let's take a look here. The next two variable is x and y. So we are supposed to find the projection of the object onto xy plane. Okay. Alright. Now, number 5, we are going to sweep second variable between two curves. This is going to be different from number 3. Two curves on projection. It's getting confusing, right? But that's okay. We are going to see how it's going to work. Two variables here. Alright. So in this case, we are going to work on the second variable. Second variable between two curves, and these two curves are going to be on the projection, not on the object. Right? Up here, two surfaces on object. But for guideline 5, step 5, you are supposed to work on projection, and it's going to be 2D, right? Projection 2D, object up here 3D. Now, once you are done with step 5, you can move to the last step, 6th step. The last step is to sweep the last variable, I would say third variable, over the whole range of projection. Okay, that's all the 6 steps you are required to follow in order to find all these 6 boundaries. Okay, so let's take a look at some illustration about how it's going to work here. What does it mean to sweep between two surfaces? What does it mean to find the projection? And how to sweep the rest of the variables. So let's take a look at this diagram here, and we are going to stick with the same order, dz, dy, dx, on this diagram, this graph. We are going to find this triple integral. Let's say we want to find the volume of this shape. We are going to use f equal to 1 here, and let's follow this order, dz, dy, dx. And now we need to find what is d. What is this d? Equal to what? All 6 of them. Now before that, let's take a look at this shape here. What does it look like? So this shape has sort of like a surface at the top, sort of like a cap, and then you have this surface at the bottom. So we have this surface at the top, sort of like a dome, okay? And with the leaf shape, the when you cut through it, you see the leaf shape. And you have another surface at the bottom, also leaf shape, and another dome at the bottom, and then you connect them together, it becomes an object, 3D object in the space. And we are going to find what this volume is. V equal to what? Volume equal to what? So let's follow the step that I give to you in the guideline. Number 1, sketch. Well, you have it right here. It's given to you, so number 1 is good. Now, number 2. We are supposed to determine the order of the integration. Now, it's given to you right here, dz dy. Oh, sorry. This is dz dy and dx. Okay, and the order is this: z, then y, and then x. Now, 3. Sweep the first variable from one surface to the other. Sweep. The first variable is z, between two surfaces on the object. Now, where is the surface? So let's take a look at z here. We are going to work on z variable, and in this graph it's going to go up and down in z direction, right? So if you take a look at the volume here, and if you want to sweep from from down to up, you are going to be sweeping from the surface down here, this curvy shape down here, to the upper shape, to the upper surface. Now you are sweeping z from the lower surface to the upper surface, lower surface to the upper surface, and you continue this throughout the range all the way through. So you can see that you start sweeping from the lower surface right here. I'm going to highlight, this is lower surface, to the upper surface right here. Okay, so let's make a note. Lower surface, that is the starting of the sweeping of z. Surface, that is z equal to f1 x and y. That is the first boundary, the boundary that we are going to put into the formula. Now, the end of the sweeping of z ends at the upper surface. Upper surface, that is z equal to this upper surface right here. By the way, this is lower surface. The upper surface is z equal to f2 xy. Okay, let me make this a little bit bigger. So we are going to do this triple integration of 1 starting from z and then y and then x. So z is going to sweep from the lower function f1x to the upper surface, which is f2x. So let's put these two boundaries into place. So z sweep from the lower surface, that is f1 x and y, to the upper surface, that is f2 x and y. So now you know the boundaries for the first variable z. Okay, now number 4, we can move on to step 4. We are supposed to find projection onto the next two variables. The next two variable is y and x, so projection onto xy plane. we are supposed to find the shadow of this shape, this object, onto xy plane, and it's shown here in the diagram. The shadow of this shape goes right down here onto xy plane. So we have the shadow right here. Now we are going to work on this shadow. Okay, now next step 5, sweep the next variable, which is y, between two curves in projection, on projection. Okay, now let's take a look at the curve here. We are supposed to sweep y, which means that we are going to go into this direction. So we are going to sweep from this one line to this line in this direction, same as y-axis. So as you can see here, this line right here has its own function, which is y equal to g1x, and another line right here has its own function, g2x. So I'm going to call this red line, red boundaries here on the projection, the left function, and this blue, the right function. Well, I can call it left curve and right curve. So we have left curve is going to be equal to y equal to g1x. That is the boundary, the starting of the sweeping of y. And then we have this right curve, which is y equal to g2x. That is the end of y sweeping. So these two boundaries are supposed to show up in the formula. All right, y starts sweeping from g1x to g2x. Okay, now last step 6, sweep the last variable x over the whole range of projection. Now you can see at this projection, and you can see that the range of x start from A to B, in this direction from A to B. So x is going to sweep from x equal to A and ends at x equal to B. So what you are looking right here is the complete formula in order to perform the triple integration, and you find all these boundaries from object found from 3D objects. Okay, now that we know about this technique, about this guideline, we can do some examples. So let's move to some examples here. So we have maybe 3 examples today. So let's start with the first one, example 1. Now we can see here that this is triple integral, and what we are looking at here, this is the f, x, y, and z. And from the order of this, you know that you are going to integrate starting from the inside to the outside, z, then x, and then y. And looking at the triple integrals, you can see that the boundaries are given to you right away. So this is good news. We don't have to find them. In this case, we can just start integrating from this term right away. And as you might have guessed, in terms of execution, it's going to be similar to the double integration, except that you have to do it one more time. So let's start working on this from the inside out. Okay, so I'm going to start integrating this triple. 0, 0, 0. It's a lot of writing. to 1x, and we have this function 4y e to the power of x squared, dz, dx, and dy. we are going to start by integrating this with respect to z. And as you can see here, there is no z in this function. It means that all other terms are going to be treated as constant. Treated as constant. So constant integrate with respect to z, it means that z is going to show up 4y e to the power of x squared. Z shows up and we have to evaluate this at z equal to 0 and x. We still have two more integrals to put in. 0, 0 and 2, 1. dx, dy. Now z equal to x is going to this x here goes into z. We are going to get 4xy e to the power of x squared. Minus 0 goes in, and you can see that if 0 goes in, everything goes to 0. So I'm going to leave it like this. Integrate this. Okay, from 0 to 1 and 0 to 2 with respect to dx first and then to dy. At this point it becomes a double integral, something you have done before. Okay, so it shouldn't be too bad, but then you see that in this case we are supposed to integrate this with respect to x, but you see x right here and x right here. It means that we need to use some sort of technique in order to solve this integration. The first thing you should think about is to use substitution. So why don't we try substitution here? What about let u equal to x squared? With this, we can find du by dx equal to 2x. Let's see if this is going to help us solve the integral. Now let's put everything in. Double integrals. 0 to 2, 0 to 1. For xy still the same, and then we substitute u into x squared. So we have eu here. dx is going to be equal to du divided by 2x, and then followed by dy. And seems like we got lucky. 2x here can cancel with 4x. This becomes 2. Right? Now, next part, we are going to have this double integrals. 0 to 2, 0 to 1 of 2y e to the power of u du, and then dy. Now we just need to integrate this with respect to u, and as you can see, exponential of u, nothing changes after integration. So you are going to get 2y e to the power of u, and we need to evaluate this at x equal to 0 and x equal to 1. X equal to 1. Right, and then we have to integrate this one more time with respect to y. 0 to 2 with respect to y. Okay, you see x right here, but then the variable that you have in your function is still u, so you are supposed to change it back to x. U equal to x squared. Alright, now it's time to evaluate this at two values. X goes in, x goes in here, x equal to 1 goes in, sorry, 1 goes in, so we have 2y e to the power of 1 minus 0 goes in, 2y e to the power of 0, so that is 1. Alright, so we have this integration 0 to 2 dy. I am going to take the common terms out, so it becomes 2y e minus 1 dy. Integrate this from 0 to 2. So next part, okay. Sorry. Alright, let me draw that again a little bit better. Okay, integrate that with respect to y, so 2y squared over 2, and now we have e minus 1 evaluate this at 0 and 2. So we can see cancellation here. 2 goes in, this becomes 4. E minus 1, and 0 goes in, everything goes to 0, so I don't need to worry about that. So in the end, this is going to be equal to 4 times e minus 1. The answer for this triple integrals. Well, you are supposed to put equal sign here. Alright. So this example, the easiest one, is easy because the boundaries are given to you. Easy because the boundaries are given to you right away, directly. Now let's take a look at example 2, a little bit more challenging to you. Okay, example 2, by the look of this diagram, you can expect something quite confusing coming out of that, but you can deal with it. So let's take a look here. What are they asking for? So they ask us to find the volume of this tetrahedron. The volume of tetrahedron. Tetrahedron is an object with 4 sides, and each side is a triangle, right? Sort of like a pyramid, but a little bit different. So with this, and instead of giving you all these the boundaries for the integration, they give you the vertices. So they give you the object in space. So they give you this first vertex. I'm sorry. Vertex, the first one is 0, 0, 0. That is the origin. Then the next vertex is 1, 1, 0 right here. And then the next vertex, 0, 1, 0. And the next one, 0, 1, 1. Now we have this tetrahedron coming out of these vertices. And we are supposed to find the volume of this object by using triple integral. Use triple integral to find the volume of this tetrahedron, of this object. Okay, as you can see, we have to use this this formula, integration triple, using this formula to find the volume, which means that we have to use function value as 1. And then we are supposed to put the differential volume here. I'm going to pick one combination, one possible combination, which is dz, dy, and dx. You can pick something else, but I'm going to stick with this for now. We have to use this formula, but the problem is we don't know the boundaries. For z, we don't know. For y, we don't know yet. For x, I made this mistake so many times, I'm sorry. dz here is supposed to be x. Okay, and we are supposed to know the boundaries for x2. And by looking at this diagram, we still don't know what the boundaries are, so we are supposed to use the guideline. So bring the guideline here. Guideline comes to the rescue. Guideline. Now let's start by the first step and go step by step after that. Number 1, the sketch. Lucky we have it right here, so sketch is done, no problem. So we see this tetrahedron, and I want you to imagine this in 3D space so that you can sort of imagine what kind of shape this is. Alright, now 2, the order of integration we know from this. We know from the order that I pick here, you can pick something else, it doesn't matter. But from here, you know that the order is this, z first, then y, and then x. Okay, number 3, we are supposed to sweep the first variable between two surfaces. So sweep the first variable here is z between two surfaces on the object. So let's find that. What surfaces are we talking about? We need to find two surfaces. So let's take a look here. We are supposed to sweep z. Z means that we are going to sweep upward and downward, z direction. So we have to find the surface that bound the upward and the lower part of this object. So let's start by the lower part of this object, the lower surface. The lower surface of this sweeping is going to be this. That is the start of the sweeping of z. So z is going to start sweeping from this surface to the upper surface right here, and it's going to be this gray surface, slanted one, from here to this surface. So the surface up here, the upper surface is going to be this surface at the top. I know it's kind of hard to imagine, but try. Think of this black surface as the base, alright, and then the red surface right here as the top. Okay, so let's define that. Bottom surface we need to translate this into equation. So let's take a look at this bottom surface right here in terms of z. Right here, z, as you can see, this is on xy plane, so z equal to 0. So the bottom surface translated into equation, this is z equal to 0. Now the upper surface, which is the red surface, upper surface, the upper plane here. Okay, we need to translate this plane into equation, and it turns out that it's given to you, which is this. Alright, and you have to express this in terms of z because you are sweeping z variable. So here z equal to y minus x. Alright, so this is the boundaries for the z variable. Two of them. Well, some of you might ask, what if this is not given to us? How do you know this is y equal to x plus z? What if we don't have this in our hand? What if we need to find this by ourselves? Well, you can do that. You can use the technique we learned maybe a few months back, maybe 2 months ago. So you can find the equation for this. We want to find the equation for this plane. I'm sorry for the mess here, but it's necessary. We are supposed to find, what if we are supposed to find the equation for this plane by ourselves? How do we do that? Alright, we can do that by using two vectors on the plane. So the first vectors, I'm going to define this first vector, u. And from this, u is going to be the destination coordinate minus the origin coordinate. So it's going to be 0, 1, 1. Now we use another vector on the plane from the origin to this vertex 1, 1, 0, and we can find the vector here by subtracting the the element of the destination to the initial point. So v here is going to be equal to 1, 1, 0. And by having these two vectors, you can find another vector that is orthogonal to both of them. So with this, you can find another vector here. I'm going to draw it like this. This vector here is going to be orthogonal to this one and orthogonal to this one. And we call this n. And we can find that by using the cross product between u and v. What about I use v cross u and get this n? So n here equal to v cross u. So let's find that using this this technique. I, j, k. And we have this v 1, 1, 0 and u 0, 1, 1. Now we perform the calculation, multiply down, I get I, and then j go to 0, and then k plus k. Now minus, multiply up, minus, I'm gonna go up here. For the first, what I just did before for the I and k, I multiply down. Up here, k goes to 0, and I goes to 0, and j not 0. So I have this. So I have this n equal to 1, minus 1, and 0. Oh, 1, minus 1, and 1. Okay, if you recall what we did before the midterm, if you have a vector that is orthogonal to both of the u and v, it means that this n is going to be orthogonal to the plane. And if you have this vector n ready, you can find the plane by using the element of n as the coefficient in front of x, y, and z. So you can find the plane here by using the element of this. So let's use that. Use the first one to be the first coefficient in front of x. Then the coefficient in front of y becomes minus 1. The coefficient in front of z becomes 1 plus z, going to be equal to some constant. And then we know that this plane passes through the origin. So let's try putting 0 in. 0, 0, 0, which means that c has to be equal to 0. So in the end, we have this equation for the plane x minus y plus z equal to 0. Or you can say that z equal to y minus x. Z equal to y minus x, just the same as what we have over here. So if it's not given to you, you can find it by using two vectors on the plane. One right here, two right here. Find the cross product to find the vector n that is orthogonal to the plane. With vector n, you can use the elements, all of them, 3 of them, to determine the coefficient in front of x, y, z of the plane. So right here, that's why you use 1, minus 1, and 1. Okay, so that's how you get this z equal to 1 minus x by yourself. Alright, but if it's given to you, you don't need to bother with this. So I need space, so I'm gonna erase what I just did down here for the equation for the plane. Alright, this has to be gone. We need space here. Alright, step 3 is done. Let's move to step 4. We are supposed to find the projection of this shape, this object, onto the next two variables. Projection onto the next two variable. We have to check what are the next two variables. This is x and y. So projection onto x and y plane. So let's take a look at this object again, but I'm going to get rid of this vector n so it's not too messy. Alright, vector u and v has to go. Okay, let's imagine looking at this object and you find the shadow of this object on xy plane, and you can tell that xy plane is right here at the bottom. So the shadow of this object on xy plane is this. Xy plane. So this is projection. Projection on xy plane. Okay, we found that. Now let's move to number 5. We are supposed to sweep the next variable, which is y, between two curves on the projection. We are going to focus ourselves onto the projection now. So we need to find the two curves. Alright, so we are supposed to sweep y. So think of this. Let's take a look here. Y is going to move right and left. So we are supposed to sweep y from two curves, as you can see here. Sweep y from this to the other side across the whole region. I'm going to use different color now. From this side to the other side, sweep y like that. And from this, you can see that it starts from this line, the left curve to the right curve. Okay, so we can say that the left curve, even though this is a straight line here, I'm going to call it curve. Left curve is going to be this line, and this line, this is y equal to x. Y equal to x. As you can see here, this is just take a look at this on just xy plane. This is definitely a line of y equal to x. So you can see here, this is line y equal to x. And then the right curve, which is going to be this. And as you can see, this curve is y equal to 1. Alright, the right curve is y equal to 1. So this is going to be used as the boundaries for the y variables. Now, sweep the last variable. Sweep x, whole range. And as you can see here, take a look at the projection. The range of x start from x equal to 0. Sweep to x equal to 1. Alright, so x equal to 0 and x equal to 1. Okay, I try my best to illustrate this on the diagram, but I know it's quite messy. Try to take your time into this. Right? Step 3 is about sweeping between two surfaces. You have to find that in z direction. In z direction. Now, after that, you are supposed to find projection and work on the projection by looking for the curves. Left and right curve here, because we are sweeping y in y direction. And in this example, y direction is left and right. That's why we found the left curve and the right curve. And if you can understand how this coming from the step 1 to step 6, then you are good to go. Okay, now we found all these boundaries. Let's put everything in place. So, triple integral. Okay, function here we are going to use 1 because we try to find the volume. And the order is dz, dy, and dx. And z, we have the boundaries available here. Z starts from 0, right here. Z equal to 0. And ends at z equal to y minus x. For y, start at x and ends at 1. Start at x, ends at 1. For x, start at 0 and ends at 1. Now that everything is in place, then it's just the integration. And it's going to be even easier than the example at this point, because the function itself is easy to work with, right? Just 1 here. So let's work on this one. Integrate 1 with respect to z, so you get z out of that. So this is equal to z. And we have to evaluate this at z equal to 0 and y minus x. And don't forget the 2 integration that is in front, 0, 1, and x, 1, dy, dx. Okay, evaluate y minus x in as z. So you get y minus x. And then 0 goes in, is nothing, so I don't need to worry about that. So I'm supposed to integrate this y minus x twice with respect to y and then x. So y starts from x to 1 and x start from 0 to 1. Okay, integrate this y minus x with respect to y. I get y square over 2 minus x y. Okay, let's continue. We are supposed to evaluate this at y equal to x and y. And don't forget the last integration with respect to x here. Okay, alright. Okay, 1 goes in. 1 goes in as y. So we have 1 over 2 equal to 1 over 2. 1 goes in as y. You have minus x. Okay, and after that we put x in as y. So we have x in as y. This becomes x squared over 2 minus x squared. Integrate this with respect to x from 0 to 1. Let's combine all these terms. Integrate 0 to 1. So what do we have here? We have 1 over 2 minus x and plus x squared over 2. Okay, integrate this with respect to x. This is easy stuff. So we have x over 2 minus x squared over 2 plus x cubed over 6, and we have to evaluate this from 0 and at 1. So 1 goes in, we have 1 over 2 minus 1 over 2 plus 1 over 6. 0 goes in, everything goes to 0. So this cancel. So here we have 1 over 6 as the final answer for example 2. 1 over 6 cubic unit. Right? They ask for the volume. You found that for them. Okay. So, all right. So this is the answer for example 2, but I'm going to explain a little bit more on this example 2 because of this diagram is so messy and you only see one of the possibilities for the order of the integration here. So you see dz, dy, dx here. Let's try some other orders. Let's see what's going to happen if you change the orders and how it affects the shape of the object that you have to look at. Okay. Alright, so let's take a look here, and we are going to try a different order of integration. So we did dz, dy, dx. We did dz, dy, and dx. Let's try another one to see the difference between what's going to happen when you change the order. Alright, so let's try dy, dz, dx. Okay, now let's follow the same guideline as always. First, the sketch right here, ready to use, no problem. Our goal here is to determine the boundaries for this triple integral in different order: dy, dz, and dx. Number 2, determine the order of this integration. We know from this new order here it's going to be y, then z, then x. Now 3, sweep the first variable, which is y, between two surfaces. Between two surfaces. So you are going to have to sweep y variable in y direction between two planes. So let's take a look here. You are supposed to sweep y across the object between two planes. So I'm going to tell you the planes starting from the y direction goes in this direction, right? It's going to have to sweep in this direction. So you have to sweep the object. And as you can see, if you can imagine this plane right here, the gray plane is going to be the left surface. This is going to be the left surface. Starting point of the y sweeping. How is that going to work? It's going to start from this plane to this orange plane, from the gray plane to this orange plane. Gray to orange, gray to orange, gray to orange. So the right hand plane is going to be this orange area. Alright, so imagine going in the y direction, going horizontally here. It's going to move from this gray plane to the orange plane. So between two surfaces, in this case we have left surface, different from example 1, right? Different from the first order that we try. In the first order we have upper plane and lower plane, the surface. Now we have left and right. Left surface, that's going to be this gray surface, and we all know this is y equal to x plus z. Y equal to x plus z. Now we have another plane, the end of the y sweeping, that is right hand surface, the right surface. And the right surface, you have to focus on this. That is y equal to 1. So this is y equal to 1. Right, so we got the boundaries for y. Y starting from x plus z ends at y equal to 1. Now find the projection. Projection onto the next two variable. The next two variable is z, x. So we have to find projection on xz plane. So find the shadow of this object on xz plane. As you can see, if you can locate xz plane on the left hand side, and if you find the shadow of this object, you are going to see that the object has this shadow on xy plane. So the shape that you are looking at here is the projection, the shadow onto xz plane. Alright, xz plane. This is projection. Okay, so in this projection we are supposed to do some sweeping. So let's do that. We sweep the next variable z, sweep next variable z between two curves in the projection. So now we look at the projection and we are going to sweep z variable. So as you can see here, z is going to sweep from this x-axis to the straight line up here. Alright, so we have one curve at the bottom and one curve at the top. So here we have bottom curve, and that's going to be z equal to 0, x-axis, z equal to 0. And now the top curve, the upper curve, that's going to be this curve right here. And this curve is explained by this equation, x plus z equal to 1. And if we want to express this in terms of z, this is z equal to 1 minus x. Z equal to 1 minus x. So we have these boundaries for z. Z starts from 0 and ends at 1 minus x. Now the last variable, x, we are going to sweep this over the whole range on the projection. And as you can see here, looking at the projection, x starts from 0 and ends at 1. So you can see x start at 0 and ends at 1. So you can put this boundaries into place. X start at 0 and ends at 1. Okay, and if you work on this triple integral, it's going to give you 1 over 6, just like the first try that we did up here. It's going to come out the same, but I'm not going to repeat that here. I just let you know that when it comes to using different order of integration, you have to change different things, many things, and specifically about how you look at the shape and how you determine the surface, the curve, the projection is, to me, I think is totally different between two cases. But using the same guideline, you can find them, no problem. Alright, now let's move to example 3. Example 3 is all about, it's the practice to help you understand how you look for the two surfaces for the first variable and look for the two curves for the second variable, and how the order of the integration affects how you look at the object. Okay, so let's start with the first one. We are going to work on this order, starting with x, then y, and then z. And we are going to find the boundaries, all of them. And just assume that we are going to find the volume of this. Okay, so first variable, dx, we are going to sweep the x variable from between two surfaces. So you look at this, and you have to take a look at the x direction. and you have to find the surfaces that that cover the whole object. So you can see that in x direction you have two surfaces, one right here. You can say that this is the top surface and this is bottom surface. Okay, two surfaces here, and with these two, x is going to sweep from this surface to this, this to this, this to this. Alright, so we are supposed to translate these two surfaces into equation. So this surface right here, this is x equal to 2, and this right here is x equal to 1. So we can put in the first boundaries here. X start from x equal to, oh, this is not x equal to 1. Alright, this is x equal to 0. Alright, so x starting from x equal to 0 and ends at x equal to 2. Alright, now we move to the next variable. When it comes to the next variable, you are supposed to work on the projection. So the projection is on YZ plane. So YZ plane, let's take a look here. The shadow on YZ plane is going to look like this. I know it looks the same as the surface that we used before for the x variable, but it's different meaning. This shadow you look at here, this is projection, and we are supposed to work on this to find how we sweep the y variable. Now we are going to sweep the y variable on this projection. So y direction goes like this. So y is going to sweep from this z-axis to this line, z-axis to this line. Alright, and this line right here, y plus z equal to 1, so you can say that y equal to 1 minus z. So as you can see here, the sweeping, y starts sweeping from y equal to 0 to the line, the slanted line, that is y equal to 1 minus z. Okay, and now the last variable is going to be the whole range of z in the projection. And as you can see here, the whole range of z in the projection starts from z equal to 0 to z equal to 1. There you go. Z from 0 to 1. So that's how you look at the object sweeping and the projection in the first order of integration. Now let's move to the next order, which is dy first, then dz, and then dx. Alright, so since I'm going to work on this order, I'm going to erase the ones that I did before. It's going to be completely different. Not completely, very different. Okay, we are going to start sweeping y variable, which means that we are supposed to work on this direction along y-axis. So we are supposed to find the plane in this direction. And if you look closely, look hard enough, you are going to see that we have two surfaces here. One is this starting point of the sweeping on this plane, and then it's going to end on this slanted plane right here, going from the left hand side to the right hand side along y direction. So y starts sweeping on from the red plane to the green plane, red plane to the green plane, red plane to the green plane, all the way through. Okay, now let's translate these planes into equations. The red plane right here is y equal to 0, and the green plane, it's given to you, y equal to 1 minus z, 1 equal to 1 minus z. So can put things in place. 1 right here. So the first boundaries are found here. Y starts sweeping from y equal to 0 to y equal to 1 minus z. The next thing, we are supposed to find the projection of this object onto xz plane. So imagine looking at this object and you find the shadow of this on xz plane. And if you find it right, the shadow is going to look like this, same as this red surface. Imagine shining lights here. You are going to see this shadow right here on this plane. Okay. Now on this plane, on this projection, we are supposed to sweep z variable. Okay, going in z direction, it's going to be like this, starting from z equal to 0 to this line up here, going in z direction. So you can see that z start moving from this line down here. I would say that is the lower curve to the upper curve up here. Upper curve up here. So the lower curve, this is z equal to 0, and the upper line or curve up here, this is z equal to 1. So put that in the boundaries for z. Z start from 0 to 1. Alright, now for the last variable, look at the projection and take a look at the range for x. You can see that x starts from 0 and ends at 2. So x start at 0 and ends at 2. Okay, so this is the result from switching the order of this integration. Now let's take a look at one more, the last one for this lecture. Okay, triple integrals again. And we are looking for the volume. So put 1 in here. The order here is z first, then x, and then y. I'm going to erase all this highlight. Okay. Now let's start over. Start with z. We are supposed to sweep z between two surfaces. Z goes in this direction vertically. So if you look at this object, you can see that the surface at the in this direction, you see surface at the top and at the bottom. At the bottom, you see this surface right here. And at the top, you see this surface right here. And sweeping of z is going to look like this, from the bottom surface to the upper surface. Bottom surface, upper surface, going up, and ends at the slanted surface, going up like that. That is z sweeping. So let's translate this into equation. The equation for the red surface down there, the lower curve, the lower surface, that is z equal to 0. And up here, we are supposed to translate this green surface into equation for z. So we have this equation already, so express it in terms of z. Z equal to 1 minus x. So let's put these two boundaries in place. Z starts from 0 and ends at z equal to 1 minus x, which is the upper surface. Now, next thing we need to do is to look at the projection on xy plane. So imagine shining light from up here, and you get the shadow of this object, and you are going to get this shadow, a shape like this. and we are going to work on this shadow, this projection to sweep x variable. So we are supposed to sweep x variable in this shadow, and as you can see, x sweep from 0 to 2, 0 to 2, 0 to 2. Two lines here, one curve at the beginning, at the starting of the sweeping, and another curve at the end of the sweeping. So we can see that the starting point is x equal to 0 and ends at x equal to 2. So put that in the integral. X start at x equal to 0, ends at x equal to 2. Okay, now the last variable, that is y, we are still working on the projection here. So y over the whole range of projection, start from here 0 and ends at 1. So you can see y, for y we start from 0 and end at 1. You can see some difference here. It changes because of the order of the integration. So I want you to practice on this. I am sorry that this drawing might not be so clear, but this is the only way I can explain this to you. It's all about the sweeping, and you have to be able to determine the two surfaces on the direction that you want to perform the sweeping. And then you find projection, and then find the two curve. Well, it all comes to the guideline I give to you. Now let's try that on the homework that I'm going to give to you along with this lecture. So the homework, this one is going to be about the double integrals in polar form, and also about these triple integrals. And it's going to be due in maybe 1 week. Okay. Well, I'm going to give you the information in the line group. Well, and that's it for today, and see you next week.